I want to talk to you today about how we develop technology at JPL and how we infuse it into flight missions. First, I'm going to give a historical perspective and introduction to robotics section at JPL. And then I'm going to talk about some component technologies that we're working on currently, which may enable future missions. Perception, navigation, and manipulation research that's actually funded by non-NASA sponsors. And then some physics-based modeling, simulation, and new mobility prototypes that are funded by NASA sponsors. And talk about the mission, talk about future mission technology that is actually funded by pre-projects, so it's directly connected to projects that we hope will take place. And then describe mission infusion pathways in general before giving us a summary of our current status with the flight projects MER and MSL. So the robotics section at JPL is about 90 people. There are 3,000 engineers at JPL, so we're actually a very small portion. But we think our footprint is actually larger than those proportions would indicate. We cover a wide spectrum of capabilities, all the way from hardware, which is indicated by 2 groups, software indicated by 2 other groups, sensors, including especially vision, by 2 other groups, and controls by 2 other groups that are dealing with specific applications that I will go on to describe. Now, over time, if you look back over the last, we've been doing a lot of looking back at timelines today, and so I wanted to throw in my own timeline. If you look back the last 20 years, actually JPL Robotics goes back more than 30 years, but if you look back over the last 20 years, you'll see 3 trends. First of all, one aspect is that we have 3 parts of the work that we do. One is doing terrestrial applications. Another is doing space applications, indicated by the blue area. And another is doing flight project involvement. Now, the flight project involvement, when I first came to JPL, was very small, and it's grown from that small amount into about half of our work today. And the other aspect of this is that in the past, we were doing a lot of manipulation work. And then because of the success we had with mobile robots, we've kind of went into a period where we were doing primarily mobile robots. And more recently, you'll see that we're getting back into manipulation a bit. The early days of manipulation, I might point out, Tony Batesy was a leader of that work. And I had lunch with Tony about a month ago, and he extended his wishes to you, so I thought I'd pass that along. So let me talk about our perception, navigation, and manipulation research for non-NASA terrestrial applications. I'm going to touch on each of these areas very quickly and not in great depth, so if you have specific questions, maybe we can address it more deeply at the end. First of all, we're participating in a DARPA program as a subcontractor to Boston Dynamics for LS3. You're probably all familiar with the Big Dog. This is kind of the follow-on to Big Dog. And we use Big Dog as part of the development platform for this work. JPL's role in this is really vision-based, where we're using vision, IMU, and legodometry in order to provide a robust estimate of the position of the vehicle. We're also using vision and visual odometry, stereo and visual odometry, in order to be able to build a local map of the environment, and then that can be used for footstep planning. And we are also responsible for providing illumination for nighttime operations. And I can give you a sense of what that looks like by the top 2 pictures. You'll see the features that are being tracked by the visual odometry algorithm, the range map is being created by the stereo vision, and then the fusion of those into a consistent world representation and specification of the obstacles that are encountered along the way, including moving obstacles such as people walking through the pathway. Now, if you take those capabilities of stereo and visual odometry and take them to the ocean, we can actually do intelligent driving of boats as well. We've married this with collision avoidance using velocity obstacles, something that Paolo Fiorini started a long time ago. We've added in an uncertainty based on the uncertainty of our position from our estimator, which includes the visual odometry. And then let me describe this picture here before I run the video. What we're adding into this is the CUL regs, which are the international regulations for preventing collisions at sea. And so this picture down here shows a green area where it's okay to go in that direction, red where you would definitely have a collision, and then purple, which is disallowed by those regulations. So in this particular movie, we had our test boat, which was driving at about 7 knots, and we had 3 other boats that were creating scenarios that were dangerous, and we had to essentially avoid them. So coming up, the first thing we want to do is pass the boat that is in front of us, so we move over to the right, but then there's another boat in a head-on pattern, so we have to avoid that one. We move further to the right. There's another boat coming at us, which is in a crossing pattern. And you see each of those boats marked by the yellow boxes as they're detected by the long-range stereo vision. The stereo vision in this case has a wide baseline, and there's 2 sets of cameras looking in different directions in order to find those. Another area of technology development that we're working on is autonomous manipulation. This is under the DARPA RMS program, and we're working with our partners at Caltech. And so this is, again, using the vision system. If you're not familiar with the RMS program, 6 teams were given a common system, which consists of a Barrett arm and hand, a LiDAR, a pair of stereo cameras, and a color imager. And then told to accomplish these manipulation tasks that are with common environments that are provided by the sponsor. And so a lot of those are particular objects that need to be manipulated in order to accomplish certain tasks. And so there is a use of the vision system in order to match models that pre-exist of the particular objects, and then paths must be planned with the manipulator system in order to accomplish this. And let me show you a particular movie. Here we see a common household drill. The idea is you have to pick this up, so you look at it first, recognize that it is a drill, specify where it autonomously specifies where to pick up the drill in order to also close the trigger that turns the drill on. Now it looks at it again in order to make sure that it hasn't shifted in the grasp, and then plans a path that not only does collision avoidance but also minimizes the torques on the manipulator, and then goes in to actually drill on a small red dot that is also seen by the vision system and successfully achieves that drilling operation. By the way, this program has just exited phase 1, and so we're very hopeful that we'll be part of phase 2. To complement these, and actually used in that particular effort, is physics-based modeling simulation, where we've used it for the manipulator system. We also have a common simulation environment, which is based on a spatial algebra framework that was developed by Abby Jane and Guillermo Rodriguez about 20 years ago. And that's been implemented into a software package called Darts D-Shell. Darts is the dynamics engine, and D-Shell is the environment in which you can create models which can satisfy a wide variety of dynamical problems. And so we use this for entry, descent, and landing simulation. We use it for surface simulation. We use it for airship simulation, formation flying. We even go so far as, with some money that we get through the National Institute of Health, with partners at the City of Hope, we're doing molecular dynamics simulation. And most recently, we've been getting funding from Johnson Space Center, their Mission Operations Directorate, to work on simulation of the future possible multi-mission space exploration vehicle, MMS-EV. And this vehicle is designed to be crewed and have manipulators which can interact with small bodies, so you're talking about low-G interactions. But we are also looking at purely robotic interactions with such bodies. And we're doing that with the athlete system. You may be familiar with Brian Wilcox's 6 limbs with 6 wheels on each limb. Each limb is 6 degrees of freedom, so it's 42 degrees of freedom total. And this was originally designed as a transport system for the lunar surface, but with the demise of the Constellation program, it's a very flexible, purpose system, and we're looking at being able to adapt it for the low G scenario of interacting with small bodies. So in order to do that, we've created a inverted pendulum crane system that offloads the mass of the vehicle and allows us to emulate the low gravity environment. And additionally, we've developed just recently this augering system, 2 augers that counter-rotate in order to prevent twist of the vehicle, and that would be designed for being able to attach the system to soft materials such as a comet. Let me just show jumping. Oh, this is the wrong movie. Okay. So this is purely based on a calculated trajectory from a simulation, but it's intended to be able to get the vehicle into a ballistic trajectory for what would be a 5 micro-G environment. And we're currently implementing force sensors onto the limbs to be able to allow us to do compliant control of the landing event as it occurs. This movie actually stops before it lands, so I'll just cut it there. So if you can't auger into a soft material, if instead you're interacting with a hard material like a stony asteroid, then we're looking at techniques for being able to attach to this. So one idea that we have is using arrays of compliant hooks that can be arranged in a radial pattern and then pressed against the surface. The hooks will get into the nooks and crannies of the rocks and allow us to grasp onto the rocks. And to demonstrate this capability, we've also done drilling where a drill was placed up through the center of that radial pattern. And so the hooks not only provide grasping force, but they also provide they compensate for the reaction force of the drilling event. And we're also looking at developing a version of this that can be used as an appendage for small robots such as the lemur system. Now, if you get into a gravity well, the athlete work and the grasping the hooks work, both of those are designed for a low G environment, but you have a kind of another low G environment, which are steep terrains, and where gravity is almost running parallel to the surface that you're interested in. And we've been unable to access these terrains, especially on Mars, where you'll see a cliff face and there's stratigraphy, and the scientists really want to be able to get there. So the idea here is to use a cable-driven system that will be lowered from the top. This axle system is one cable with and then 2 wheels on the rover. But there's the ability to have that deployed in a number of different ways. One is that you can have precision landing near a crater and then drive over the edge off the lander. Another is that you can have this as a kind of marsupial system where it's attached to a larger vehicle like an athlete. Another is that you put multiple of these together in order to form a multi-wheeled vehicle. And so I'm going to show a movie of our efforts with this dual-axle concept where we can provide that kind of capability. And I'm going to skip ahead. So here you see the axle system driving over fairly rough terrain. That slope is probably about 30 degrees, which is usually the limits for our rovers. In this particular version, it does skid steering, although we're working on other ways in which to attach the bodies in order to provide non-skid steering. So here you see a detachment of the one axle system in preparation for going over the cliff. And I'm going to speed this up a little bit to show you how it goes down over the steep terrain. And then inside of the wheels are these donuts, and the donuts have 4-bar linkages which open up panels that deploy instruments for sensing the environment and doing the scientific research. And then you continue all the way down the terrain, go back up, it's a reverse pattern, and re-engage with the vehicle and drive away. So let me talk about some technology that we're developing specifically for future mission concepts. The first of this is terrain relative navigation. So very similar to the visual odometry techniques where you're trying to find out your position as you're migrating, moving across the surface. Here you're trying to find out your position as you're going down towards the surface. And so the prerequisite for this is that you are in orbit, you build up a map of the terrain from orbit, and then you match against that map as you're going down in the landing event. And what this technology enables you to do is take what is currently the smallest landing ellipse, which we're going to have for the MSL system. It's going to be about 30 kilometers for the major axis of the landing ellipse, and shrink that by 2 orders of magnitude down to about 300 meters. And then within that 300-meter landing ellipse, we're also working on another technology which is called hazard detection and avoidance, HDA. And so you would be able to have a very quick divert maneuver to be able to avoid a very large boulder that existed inside of that 300 meters, just to prevent a catastrophe from happening. Another mission-specific technology, so once you get down to the landing event, you're inside of this landing ellipse, then you have to rove out of the landing ellipse, because typically the scientists are interested in the rough terrain. You're landing in the smooth terrain, the scientists want to get out to the rough terrain, which is where all the rocks are, and that's where all the geology is. So we've been trying to speed up the pace of the rovers, and this is done by taking those same algorithms of stereo vision and visual odometry, which were very computationally intensive, putting them into an FPGA, which is very low power, and using that as a coprocessor on the system. This allows you to continuously drive, as opposed to drive and then process for a very long duration, and then drive and process. Typically, those steps for like the MER rovers, you would be driving for a few tens of seconds, and then you'll be sitting processing for 2 to 3 minutes. And that slows down the pace, and it also burns a lot of power, because the vehicle still has its keep alive power during that period. If you can drive continuously, then you become much more power efficient, as well as achieving the mission objectives more quickly. And on top of all that, if you can compute stereo and visual odometry very rapidly, then you get those for free as you're driving along. You become a much more safe vehicle as you're able to detect not only the geometry of the environment, but whether you're having any sinkage or slippage events. And so this is what this looks like. And so what you see here is the Gestalt algorithm, which is the standard MER rover navigation algorithm, but now the vehicle just stops and does its execution of the wheels immediately after turning the wheels. Now, one thing to note about this is that MER and MSL have bank switching of the motors. They don't have enough motor controllers on board in order to be able to steer and drive at the same time. And so by bank switching, that means you can either steer or drive. And so that's the kind of behavior that we've seen here. It is possible in future rovers that we will be able to do steering and driving. In this case, this becomes a continuous motion. Another capability is, once you've gotten out of the landing ellipse and traversed quickly across the terrain, the real objective is to do some analysis of the terrain. And so we're looking at possible sampling operations that would involve coring into rocks, extracting those cores, placing them into a containerization system. And so we're prototyping that containerization system. Here you see a drilling system that provides a core about the size of a stick of chalk, if anybody remembers school days. And the core is actually encapsulated in a sample tube that is inside of the core bit. That whole bit assembly gets placed into a receiving receptacle that's a carousel on this prototype system. And in this case, there's 4 carousels, and this white is actually a prototype plastic bit. That gets rotated in place so that this service arm can extract out the core bit, place a cap onto the sample tube, and then place it into the cache. And so let me show a quick movie of that kind of system in action. And I'll speed it up just for the sake of brevity, but here you see the transfer arm going to the back side of a specific core tube, extracting the core sample container with the rock in it, bringing that over to extract a cap from the outer ring of the carousel, and then moving that over to the capping station for a capping operation, which is intended to hermetically seal this, and we're working on different technologies for that hermetic sealing. And then it sticks it into the central area, which is the canister that would contain all of the samples, and that is actually extracted, can be extracted from the system through the backside and deposited on the surface of Mars, where it is picked up by a fetch rover at some future mission. Now, another technology for mission specific was sampling as well, but in this case, the lunar sampling. And I mentioned this, and specifically, we had this exercise recently to develop a mission sampling concept, and DLR participated in that by providing the cameras that went onto the mock-up lander. Those cameras provided a mesh of the terrain in front of the lander, which was used for selection of the digging sites. And then this system was very similar to our Phoenix mission, where we would do digging on the moon instead of on Mars. The material that was obtained was sifted, and the extracted components were placed into a canister. The canister, its contents is verified using a pressure sensor, and then once a full canister exists, it can be placed into a capsule, which is intended for launch off of the surface. So let me talk about infusion pathways for all of these technologies. First, point out how we've infused technologies in the past, specifically into MER and MSL. So I've already talked extensively about our use of stereo vision, visual odometry, and navigation. That's all consistent with what we've used on MER. And it's important to point out that through our research work for many years, we had matured the technologies such as stereo vision and visual odometry to the point where the flight projects saw them as of minimal risk and were willing to adopt them for the baseline of the mission. Additionally, we've done this similar kind of maturation of technologies for manipulation and instrument placement. So here we see visual target tracking. We've done instrument placement with collision avoidance of both the structure of the vehicle as well as the surrounding terrain based on the known models of the vehicle and the stereo vision system. Standard manipulator control for instrument placement, and we'll be doing forceful interaction with the environment in upcoming MSL where we're doing drilling. We've done the first of what we call autonomous science, which is really trying to triage the science data that's collected in order to send back the best first. And so one way to do that is when we got onto Mars and we started to see these dust devils going across the surface, the question is, how do you catch a dust devil? And instead of sending back tons of images and having the scientists look for those, can you just do some image differencing on board and then notice that something moved in this image? And so we were able to send back very rapidly only the images that had dust devil events. We've done visual analysis for EDL, entry, descent, and landing, and this is similar to what I was talking about before, but what we did here is it was a very quick win with a very slow processor. We were only able to take 3 pictures on the descent and match 2 feature points across 3 images and be able to then determine whether the vehicle was moving with a lot of velocity across the surface, too much velocity that might shear the airbags, and we were successful in essentially averting that problem. And in fact, the opportunity landing would have probably sheared the airbags had not the retro rockets on the back shell been fired differentially to compensate. Finally, we've developed operation tools both for mission operations for the scientists and for engineers, so we can both, those tools came out of a lot of technology development and were finally adopted by the projects and now are the standard suite of tools used for most of our Mars missions. So let me talk about NASA's infusion pathways right now. You may be familiar or may not be familiar with the National Research Council's decadal survey, which is what NASA asks the scientists of the US, what should we do next? And so they go off every 10 years and create that set of objectives. The most recent decadal survey was done this past spring, and the scientists came back to the Science Mission Directorate of NASA and said that we think you should do three things. You should have flagship missions, New Frontiers missions, and Discovery missions, and they specified funding levels for each of them, where the flagships would be on the order of $2.5 billion, the New Frontiers would be on the order of $1 billion, and the Discovery programs would be on the order of $500 million. And all of this information you can find on the web. But what I tried to do here was to highlight in blue the missions that have potential robotics content to them. And so what we're trying to do, and what you could do if you go through the technologies that I've just presented and match them against these missions, is you'll see that there's a correspondence. So what we're trying to do is work on technologies that are consistent with what the scientists want and get the scientists on board, because they are ultimately the customer. We've talked a little bit today about customer focus on for the commercial sector. Well, customer focus for the space sector is important too, and that customer for science exploration is the scientists themselves. And then there's two other offices of NASA, the Human Exploration and Operations Office and the Chief Technologist Office, and they also have obviously an interest in technology, wide spectrum of technology, and hopefully that includes robotics technology. And I've highlighted those in blue also where we feel like we can contribute, including the International Space Station and the Advanced Exploration Systems that I've described before, the MMSCV and similar. In the Chief Technologist Office, there are three phases that correspond to basically low technology readiness level, mid technology readiness level, and higher. And those are the early stage, game-changing, and cross-cutting. And we've been recently working on a NIAC result. We won a NIAC proposal to work on comet sampling, and so we're working on that program already, and the other two programs we're hoping to get involved in. And JPL is actually involved in the cross-cutting program, but not in the robotics area at the current time, so there's opportunities to be explored. So now I've talked about how we're developing technology and how we're putting it into the missions. I thought I'd end with just a quick update of the missions that have been our major target for technology infusion in the recent past. And Opportunity is the last of there were two MER rovers. Spirit has died essentially, and Opportunity is still alive and kicking, and we're very happy about that. And it's now been, since 2003, it's gone 2,770 sols total on Mars, 34 kilometers total driving distance, and we never thought we would get there, but we finally reached this Victoria crater. It's a very large crater, and we're just on the edge of it. And the biggest challenge we have in the near term is that this crater is just below the equator, and we're entering the Martian winter. So Martian winter, or the solstice, is on March 30th, and we need to make sure that our solar panels are pointing northward in order to supply us with enough power. So if you see this Cape York feature here, we have since driven from our initial position down here up towards this north side, where there's a little bit of a slope. Even though the major slope of the crater is toward the south, that hillside has a slope to the north, and we'll probably be hanging out there for the next several months in order to be able to make sure that we have enough power. So that's the status with Opportunity. MSL, if you don't know, MSL is our next big system. It's about the size of a small car. It's about 1 metric ton in mass. And just to give you a sense, the arm on MSL is about the same mass as the entire MER system. And this is when we were doing the final development and testing at JPL. And then the whole rover was packed up and shipped to Kennedy Space Center. It was brought out of its box. Final checkouts were done. Down here, you see the way it was placed in its stowed configuration with the bogies folded up. And then the descent stage, which will lower the robot to the surface, essentially enshrouds the robot, hangs over the side, and has propulsive engines in order to be able to hover over the surface while the robot is lowered to the surface. After the descent stage was placed on top of the rover, the back shell was placed on top of it, and then to complete the Russian doll, you have the A heat shield is attached on the bottom, and the cruise stage goes up around the top of the back shell. And finally, the fairings were placed. You see in the photo one fairing placed to encapsulate this, and the whole assembly has been placed on the rocket and is now sitting on the pad at the Cape. And so launch, just so you, in case you didn't know, the launch was originally supposed to be this Friday. It's now scheduled for Saturday, as far as I know. It's 4 o'clock Munich time, 10 a.m. East Coast time. And our next stop is Gale Crater on Mars. So thank you very much.